Today we'll talk about physics. We began a new book from Kepler, the same from the other one, the other book, last book we finished. It's called the second volume of Physics, Gravitation, Waves, and Thermodynamics, right? And the first unit it's about gravity. And so we've studied what is gravity. And but here is in more depth. So there's this guy, and he's very good. And in 1543, yeah, in 1543, that guy, in 1543, there was a model of Copernicus that was heliocentric. But what I'm trying to say is that from 1571 to 1630, oh, sorry. Johannes Coupler was born, and he was a very good astronomer, and he did the calculations very accurately. And he had like a nemesis that was called Tycho Brahe, and he had been watching the night sky for a long time, and he had lots of numbers. And Kepler asked for Tycho Brahe to give him the numbers so that he could find a constant. That is the Kepler constant. And so he said, I have a body, and there is another body over here. Actually, I'm going a little bit too fast. There was this belief that the Earth was the center of everything, and then we had the sun and the other planets going around the Earth. And actually, it was thought that the Earth was like the orbits were circular, so it was a circle around the Earth. And then came Copernicus and said, no, it's all wrong. The sun is in the middle and everything is around the sun. And then the Catholics, they were against Copernicus because they were religious and they thought that the Earth was supposed to be the center of everything. And then came Kepler and said, no, Copernicus is right because of science. They made calculations and all, but instead of being circles like the Greeks thought, because a circle is like it's a symbol of perfection. Actually, it's an ellipsis. And so it's something like that. It would be something like, here's the sun, and the planet would do something like, I mean, it's exaggerating, but something like that. All right. And Kepler made some laws. The first law is that all planets move in elliptic orbits with the sun, and the sun is one focus. So an ellipsis has two focus. Then we can draw the ellipses like this. One would be the sun and the other one would be the planets, right? The second one is that there is a line that connects the Sol to a planet that has the same area in same equal times. So what it's saying is that we have the sun here, and there is a line, and the planet is here. So it says that this area over here, right, is the same as this area over here. Oh, is this area over here. It's just that this one is, it has a not so big theta, it's an angle, but it's far away, and this has a big angle. I did it wrong, it's a big angle, but it's near the sun. And that the square of the revolution period of any planet is proportional to the cube of the distance to the sun of that planet. So what it's saying is that d squared is equal to r cubed. And also we have studied, and then came Newton after him and said, we know that we have elliptic orbits, but we know how the planets move, but why do they move? And it's because of a force called gravity. So gravity is a force that attracts two bodies, right? And so that force of gravity, F, is going to be a gravitational constant, G, the mass of one body times the mass of the other body divided by their distance squared. So the further apart, the less force there is because we're dividing, right? And the bigger one mass is, the stronger it will be. This is 6.67 times 10 to the negative 11 Newton times meter squared divided by kilogram squared. It's a constant, right? And from this, we can derive acceleration, right? We know that acceleration is force over mass. And here's where comes the gravity. And so that's the force that pulls the planet to the sun and the sun to the planet. And all right. And now another thing that we need to know is we have a mass, and the bigger the mass, it's proportional to the force of the gravity. So if a big mass has a big gravity and a small mass has a small gravity force. So now let's do some examples. Right. So we have, say there is a small planet with a revolution period of 5 years. What's the distance from it to the sun? So we have the sun and this unknown planet. There's an elliptic orbit, you know that. And we have a certain radius r. And we know that the period it takes 5 years. And so we know that t squared is equal to r cubed. So t is equal to square root of r to the third. But actually, it wants to know the radius. So we know that r is equal to the cubic root of t squared. And so the cubic root of 25, let's just plug it in. The cubic root of 25 is the same thing as 25 to the 1/3. Oops. 25 to the 1/3 is 2.92. So it's 2.92. Now that radius was in this case like meters, not meters, right? Like megameters, or any one that would be given. Yeah. Also, we have, yeah, just something like that. So Uranus has a moon called Umbria that its radius is 267 megameters, and the revolution period is a constant there. Find the period of another moon called Oberon that has a radius of 586 megameters. Same thing. T is the square root of 586 cubic. 586 to the cubic, square root of answer, that's 14.8185. All right. Now it says I want what is you use the value known of G to calculate the mass of Uranus. And so I told you before that F is equal to G m1 m2 over r squared. Right. But we can rearrange it to know for a better way. And so we have that the force let me go. Oh boy. Here. We have that the force is equal to m times. All right. And so the force that it's Gm1, let's say like m sun, m planet, here m planet, Gm over r squared, that's equal to m times a. Now we know that it's an orbit, and the orbit would be an omega, right? And the omega is v squared over r. Looks like a v. Be a v squared over r. Your r squared. Oh. r squared. And when we multiply, then this cancels out with this and this. And this with this. Right, and we have G M sum over R. That's equal to V squared. Right? And we know that V is equal to 2 pi R over T. That that came from T is equal to what I did was the whole C, the circumference, over the velocity I had. And so with that, we can do 2 pi r squared. I can change up here. 4 pi squared r pi r squared t. And so if we rearrange this, we get that t squared is equal to 2 pi r squared times r over g m sum, or just m. Now, so this turns out as r cubic, and this is 4 pi squared. All right, pretty good. And now it wants to know the mass. So mass is equal to 4 pi over g d squared m. Now, all right. Let's see what we have. We have that we have 4 pi over 6.67 times 10 to the negative 11 times now let's see. So sun to Uranus in megameters. The size 699. Yeah, the r cubic would be 586 to the cubic, right? And the t we found to be 2.92. and just do the calculations. But that's it.